Here's a solved example where we apply the KKT conditions, and there are two inequality constraints in the constraint optimization problem. So the objective function is minimize x1 minus 2 squared plus twice x2 minus 1 squared, subject to the inequality constraints x1 plus 4x2 is less than or equal to 3 and x1 is greater than or equal to x2. In standard form, the objective function doesn't need to be changed, and the constraints are g1 x1 x2 is x1 plus 4x2 minus 3 is less than or equal to 0, and x2 minus x1 is less than or equal to 0. We construct the Lagrangian L x1 x2 lambda 1 lambda 2. We have two lambdas corresponding to the inequality constraint. This is the objective function, and then lambda 1 times g1, which is x1 plus 4x2 minus 3 plus lambda 2 times g2, which is x2 minus x1. The derivative of the Lagrangian with respect to x1 and x2 is this. With respect to x1, when we differentiate this, we get twice x1 minus 2 from here plus lambda 1 plus minus lambda 2, because we have a negative sign here. And when we differentiate with respect to x2, we get 4 x2 minus 1 plus 4 lambda 1 plus lambda 2. So this is del of the Lagrangian. I have throughout this presentation used the top half to keep the relevant portions of the KKT conditions so that we can look at them. Now, this is a plot of the contours of the function f of x1, x2 equals x1 minus 2 squared plus 2, x2 minus 1 squared. This is the minimum of the objective function, and these contours correspond to constant values of the objective function. The further away we go, the higher the value of the objective function. This green line here represents g1 equals 0. This is g1, x1 plus 4, x2 minus 3 equals 0. And on this side, it's infeasible. So the bottom left side of this green line is feasible. And this brown line corresponds to x2 minus x1 is less than or equal to 0. On this side, x2 minus x1 is greater than 0. That's infeasible. So it's this side where the second constraint is feasible. And therefore, because of the presence of two constraints, we have this whole region is infeasible. And this is the feasible region. That's the global minimum. Let's list out the KKT conditions from the Lagrangian. The primal feasibility condition is that g1 of x1, x2 is less than or equal to 0, and g2 of x1, x2 is less than or equal to 0. The dual feasibility conditions are lambda 1 and lambda 2 must be greater than or equal to 0, because they correspond to two inequality constraints. And the complementary slackness conditions are lambda 1 x1 plus 4 x2 minus 3 equals 0, and lambda 2 x2 minus x1 equals 0. And since we have two inequality constraints, we have four possible cases to examine. Case 1 is when both lambda 1 and lambda 2 are zeros, that is when both constraints are inactive. Case 2 is when g1 is active, but G2 is inactive because lambda 2 is still 0, lambda 1 is greater than 0. Case 3 is when lambda 1 equals 0, so G1 is inactive and lambda 2 is greater than 0, so G2 is active. And case 4 is when lambda 1 and lambda 2 both are greater than 0, therefore both G1 and G2 are active constraints. And from the previous slide, we saw the derivatives. Therefore, equating the derivatives to 0, we have twice x1 plus minus 2 plus lambda 1 minus lambda 2 equals 0, and 4 x1 minus 1 plus 4 lambda 1 plus lambda 2 equals 0. So these are our KKT conditions. And this is a bigger graph showing the same x1, x2 plane, and this is one of the constraints, the green line, that's x1 plus 4, x2 minus 3 equals 0, and this brown line is x2 minus x1 equals 0. The contours are those of the objective function f of x1, x2 equals x1 minus 2 squared plus twice x2 minus 1 square. This is the x1 axis, and it says y here, but this is the x2 axis. The infeasible region is shaded gray, and the feasible region is white. Case 1, when lambda 1 equals 0 and lambda 2 equals 0. So none of the constraints are active. Now, when none of the constraints are active, stationary condition simply implies that the derivative of the objective function is 0, which means that it's the global minimum. So let's replace lambda 1 and lambda 2 with zeros in the stationary conditions. And so we get twice x1 minus 2 equals 0 and 4 times x2 minus 1 equals 0, whence we get x1 equals 2 and x2 equals 1. So this is our first candidate solution. We have to test the feasibility conditions to see if they are satisfied. Unfortunately, G1, x1, x2, if you replace the values of x1 and x2 with 2 and 1, we get 2, which is greater than 0. So G1, the first inequality constraint, is being violated. We have to discard this case. Let's look at it geometrically. So this is the global minimum, and the solution is at the global minimum. X2 equals 1, x1 equals 2 and x2 equals 1. And we can see that it's in the infeasible region, which is shaded gray. Discard. Case 2, when lambda 1 is greater than 0, lambda 2 is equal to 0. In this case, this is an active constraint because lambda 1 is greater than 0. G1 is an active constraint. So we have three variables, lambda 1, x1 and x2 to solve for, and we have three equations. Dropping the lambda 2, we get two equations from the stationary condition, and complementary slackness also must be satisfied, so we have our third equation. This is from complementary slackness, and these are from the stationary conditions. Solving, we get x1 is 1 whole 2/3, x2 is 1/3, and lambda 1 is 2/3. And we already know that lambda 2 equals 0. Let's check if the feasibility conditions are satisfied. G1, x1, x2 equals 0 because we used it to solve. And G2 is x2 minus x1, which is less than or equal to 0. So that's also satisfied. Let's keep this. Let's look at it geometrically. This is x1 is 1 whole 2/3 and x2 is 1/3. Which point is this? It's this point marked star. In fact, it will be the global minimum, as we will later see, but for now we'll pretend that we don't know it's the global minimum. It's one of our candidate solutions. Let's retain this solution. Case 3 is when lambda 1 equals 0 and lambda 2 is greater than 0. So this is an active constraint. x2 minus x1 must be equal to 0. G1 is active, so x1 minus x2 equals 0, same thing. And from the stationary conditions, we get these equations, substituting lambda 1 with 0. So what we now have 3 variables to solve in 3 equations. 2 from the stationary conditions, and one of the equations is x1 minus x2 equals 0. Solving, we get x1 is 1 whole 1/3, x2 is 1 whole 1/3, they have to be the same. Lambda 1 is 0, obviously, and lambda 2 is, solving, we get negative 1 whole 1/3. So lambda 2 is negative, but dual feasibility says that lambda 1 and lambda 2 both have to be greater than or equal to 0. So feasibility is violated. Let's look at it geometrically. This is what we got. And obviously it's in the infeasible region. x1 is 1.33 and x2 is also 1.33 at this point. Case 4 is when both lambda 1 and lambda 2 are greater than 0. So both the constraints are active. From the complementary slackness conditions, we get this equation, x1 plus 4x2 minus 3 equals 0, and x2 minus x1 equals 0. And from the stationary conditions, we get twice x1 minus 2 plus lambda 1 minus lambda 2 equals 0, and 4x2 minus 1 plus 4 lambda 1 plus lambda 2 equals 0. So we have 4 variables, x1, x2, lambda 1, and lambda 2, and we have 4 equations to use. So solving, we get x1 is 3 over 5, x2 is 3 over 5, lambda 1 is 0.88, so far so good, but lambda 2 is negative 1.92. So again, dual feasibility is being violated. So we reject the solution. So geometrically, this is our solution. Now this is an interesting case. The primal feasibility is not being violated. In fact, both the constraints are active constraints. So why is it that we have to discard the solution? What is the implication of lambda 2 being negative? Let's look at that. So let's look at the stationary condition. Del F plus lambda 1 del G1 plus lambda 2 del G2 must be equal to 0. Now, this is del F. It's pointing away from the global minimum. Del G1 must be orthogonal to the green line, and del G2 must be orthogonal to the brown line. And you can see that no way will del G, a combination of del G1 and del G2 with positive weights lambda 1 and lambda 2 make this stationary condition be satisfied. So this is a valid solution, but it's not optimum. So the final solution is case 2. Del of fx1, x2 is this, negative 2/3 times 1, 4, which is the vector x1, x2 here, and del g1 is 1, 4, this vector. And they cancel out if this is the weight, lambda 1. This is the MATLAB code for the plots I have generated.